Welcome to Astronomy Daily, your source for the latest space and astronomy news. I'm Anna.
And I'm Avery. We've got another stellar episode lined up for you today, Monday, January 26th, 2026.
That's right. Today, we're taking you on quite a journey through the cosmos. We'll be exploring two fascinating Mars stories that paint very different pictures of the red planet's future, from terraforming dreams to atmospheric water harvesting for survival.
Plus, we've got some incredible discoveries from across the universe. We'll reveal how NASA's Chandra Observatory has cataloged over 1.3 million X-ray sources, discover an ingenious new use for earthquake sensors that could save lives, and uncover why those water worlds we've been excited about might actually be lava planets in the skies.
And we'll finish with a breathtaking look at our cosmic future, courtesy of the James Webb Space Telescope's latest images of a dying star. So settle in, because we're about to explore the universe together.
Let's get started.
Avery, let's kick things off with what could be one of humanity's most ambitious projects ever. Scientists are saying it's time to take terraforming Mars seriously, and they've got a roadmap to make it happen.
This is fascinating stuff, Anna. For decades, terraforming Mars has been the stuff of science fiction. But new research suggests we might actually have the tools to pull it off. A team of planetary scientists, biologists, and engineers has published what amounts to a blueprint for transforming the red planet into a habitable world.
What's really interesting is the timeline they're proposing. This isn't a quick fix. We're talking about a multi-generational project that could take centuries. But the key breakthrough is that they believe we can use resources already on Mars rather than shipping everything from Earth.
Exactly. The plan has three distinct phases. Phase 1 is all about warming the planet. Right now, Mars averages around -70 degrees Celsius. The scientists propose using engineered nanoparticles made from Martian dust, shaped like tiny rods and released into the atmosphere. These particles would trap escaping heat and scatter sunlight towards the surface, potentially warming Mars by more than 30 degrees Celsius.
And here's the clever part. This method is over 5,000 times more efficient than previous terraforming schemes. University of Chicago planetary scientist Edwin Kite, one of the study's co-authors, notes that Mars was habitable in the past. So greening Mars could be viewed as the ultimate environmental restoration challenge.
Phase 2 brings in biology. Once temperatures rise enough to melt some of Mars's vast ice deposits, scientists would introduce genetically engineered extremophiles, hardy microorganisms that can survive in the harshest environments. These pioneer species would kick off ecological succession, creating organic matter and slowly changing the chemistry of the surface and atmosphere.
And the final phase is the longest and most ambitious, building a stable biosphere with oxygen-rich air. The goal is a 0.1 bar oxygen atmosphere, which would be enough to sustain human life without pressure suits. Harvard planetary scientist Robin Wordsworth puts it beautifully. Life is precious. We know of nowhere else in the universe where it exists. We have a duty to conserve it on Earth, but also to consider how we could begin to propagate it to other worlds.
But this isn't just about making Mars habitable. Nina Lanza from Los Alamos National Laboratory sees Mars as a prime testbed for planetary engineering. She suggests that if we want to learn how to modify our environment here on Earth to keep it habitable, maybe it would be better to experiment on Mars first, rather than being too bold with our home planet.
Of course, there are serious ethical considerations. As Lanza points out, if we terraform Mars, we'll really change it in ways that may or may not be reversible. Mars has its own history, and we might lose the opportunity to study how planets form and evolve in their natural state.
The researchers stress that we need to start preparing now, even though actual terraforming is still far off. Upcoming Mars missions in 2028 or 2031 should include small-scale experiments to test these strategies, such as warming localized regions. Any technology deployed must be reversible, controllable, and biologically safe.
It's an audacious vision, but as the team points out, 30 years ago, terraforming Mars wasn't just hard, it was impossible. Today, with advances in technology and our understanding of Mars, it's becoming a real possibility. Whether we should do it is a question we'll need to answer as a civilization.
Sticking with Mars, Anna, our next story takes a more immediate look at how future astronauts might survive on the red planet. New research suggests that the Martian atmosphere itself could provide a vital backup water source.
This is really practical thinking, Avery. While underground ice remains the most promising long-term water source for Mars missions, scientists are now exploring atmospheric water harvesting as an adaptable solution for scenarios where subsurface resources are inaccessible.
The study, led by Dr. Vasilis Anglizakis of Strathclyde University and published in Advances in Space Research, emphasizes building a self-sufficient water infrastructure. As Dr. Anglizakis explains, reliable access to water would be essential for human survival on Mars, not only for drinking but also for producing oxygen and fuel, which would reduce dependence on Earth-based supplies.
The challenge is that Mars's atmosphere is extremely thin and cold. But it does contain trace amounts of water vapor that could be collected and condensed using specialized technology. The study introduces novel approaches inspired by Earth-based dehumidification and sorption technologies.
What makes this particularly valuable is the flexibility. While underground ice deposits are seen as the most practical long-term solution, their accessibility is limited, especially near likely landing zones for human missions. Since the precise location of usable ice is uncertain and excavation technology is still evolving, having alternative sources is essential.
Atmospheric water harvesting offers a mobile, adaptable alternative. The equipment would be portable, making it a compelling addition to the toolkit for sustaining human life on Mars. As Dr. Anglizakis notes, this study is one of the first to compare the various technologies that could be deployed to recover water in a Martian environment.
The key takeaway is that future Mars missions will require not just one solution, but a layered approach. Combining underground ice extraction, soil moisture recovery, and atmospheric harvesting will allow missions to adapt to different environmental and logistical conditions.
While the process is energy intensive, atmospheric harvesting can serve as a crucial contingency, especially in emergencies or during long-range missions. The research offers insights that could make future space exploration missions more self-sufficient and sustainable.
It's this kind of practical, multifaceted planning that will ultimately make long-duration Mars missions and potential colonization efforts successful. Every backup system counts when you're 225 million kilometers away from home.
From the red planet to the entire cosmos, Avery, let's talk about NASA's Chandra X-ray Observatory and its incredible catalog of cosmic recordings.
Anna, this is like the ultimate astronomical music collection. The Chandra Source Catalog now contains over 1.3 million X-ray detections across the sky, representing 22 years of observations from one of NASA's great observatories.
The latest version, called CSC 2.1, contains data through the end of 2020 and includes over 400,000 unique, compact, and extended sources. This catalog is a treasure trove for scientists, providing everything from precise positions in the sky to detailed information about X-ray energies.
What makes this particularly valuable is that it allows scientists using other telescopes, both on the ground and in space, including NASA's James Webb and Hubble telescopes, to combine Chandra's unique X-ray data with information from other wavelengths of light.
To illustrate the richness of this catalog, NASA released a stunning new image of the galactic center, the region around the supermassive black hole at the heart of the Milky Way, Sagittarius A star. In just a 60 light-year span, Chandra has detected over 3,300 individual X-ray sources.
That's incredible when you think about it. 3,300 sources in what amounts to a pinprick on the entire sky. This image represents 86 observations added together, totaling over 3 million seconds of Chandra observing time.
They've also created a fascinating sonification of the catalog, translating the astronomical data into sound. The sonification encompasses the new map that includes all of Chandra's observations from its launch through 2021, showing how X-ray sources appear and reappear over time through different musical notes.
In the visualization, each X-ray detection is represented by a circle, and the size of the circle is determined by the number of detections in that location over time. You can see the core of the Milky Way in the center and the galactic plane stretching horizontally across the image.
And here's the exciting part. Since Chandra continues to be fully operational, the catalog keeps growing. The video transitions to and beyond after 2021 as the telescope continues to collect new observations.
This catalog represents decades of cutting-edge science and will continue to be an invaluable resource for astronomers studying everything from stellar evolution to the nature of black holes. It's a testament to the longevity and continued productivity of the Chandra mission.
Now for something completely different, Avery. Scientists have found an ingenious new use for earthquake sensors tracking dangerous space debris as it falls back to Earth.
This is such a clever solution to a growing problem. Every year, thousands of discarded satellites orbit our planet, and an increasing number are falling back into Earth's atmosphere. While most disintegrate before hitting the ground, some survive long enough to pose real dangers.
Researchers from Johns Hopkins University and the University of London have demonstrated that existing seismic monitoring networks can track these falling satellites with remarkable accuracy. The investigation was led by Benjamin Fernando, a postdoctoral fellow at Johns Hopkins, who studies seismic activity on both Earth and other planets.
Here's how it works. When falling objects re-enter Earth's atmosphere at high speed, they generate sonic booms. These sonic booms create shock waves that ripple through the ground, and seismometers can detect this seismic energy just like they detect earthquakes.
The team demonstrated this by analyzing the April 2, 2024 re-entry of China's Shenzhou 15 orbital module. This module was about 3.5 feet in diameter and weighed over 1.5 tons, definitely dangerous if any component reached Earth's surface.
Using 127 seismometers in Southern California, they tracked the module as it traveled at hypersonic velocities between Mach 25 and Mach 30, roughly 10 times faster than the world's fastest jet. From the seismometer data, they reconstructed the object's trajectory, determining it followed a northeasterly path over Santa Barbara and Las Vegas.
What's particularly impressive is that their reconstruction placed the flight path about 25 miles north of the predicted re-entry path from orbital tracking alone. This highlights the limitations of current tracking methods once objects enter the denser parts of the atmosphere.
The seismic data also revealed the breakup pattern. Initially, the signals showed the spacecraft was mostly intact during its high-altitude trajectory. Later signals indicated complex waveforms showing fragmentation, about 8 to 11 unique breakup events within just 2 seconds.
This gradual degradation pattern is crucial information. It suggested that dense, reinforced components likely survived long enough to reach the lower atmosphere, increasing their chances of landing intact.
Beyond just tracking where debris lands, this method addresses environmental concerns. Falling debris can produce tiny particulate matter containing toxic propellants or radioactive materials. For example, Chilean scientists found man-made plutonium in a glacier that they suspect came from the Russian spacecraft Mars 96, which disintegrated in 1996.
The ability to track debris in near real time, providing accurate locations within minutes instead of days or weeks, would help authorities respond faster, protect people, and identify hazardous materials. It could also provide aircraft warnings and support environmental monitoring.
As Fernando points out, as launches increase and more large satellite constellations reach the end of their design lives, tools like this will become increasingly important. We need as many different ways as possible to track and characterize space debris.
Avery, our next story is going to make exoplanet hunters rethink some of their most exciting discoveries. It turns out that 98% of what we thought were potential water worlds might actually be lava planets.
This is a real wake-up call for the scientific community, Anna. New research led by Rob Calder at the University of Cambridge suggests that nearly all known sub-Neptune exoplanets, previously thought to be potential ocean-bearing Hycean worlds, are far more likely to be composed of molten rock.
Sub-Neptunes are the most commonly discovered type of exoplanet, larger than Earth but smaller than Neptune, yet their exact nature has remained elusive because our solar system offers no direct equivalent. Understanding what these worlds are made of is crucial for the search for life and for refining our models of planetary formation.
The problem stems from what scientists call degeneracy, when one set of observations can be interpreted in multiple ways. Take the case of planet K2-18b. Researchers celebrated its methane-rich ammonia-poor atmosphere as evidence of a Hycean planet with thick hydrogen atmosphere overlying vast oceans.
But here's the twist. Calder and his team point out that molten rock can also dissolve ammonia, just like water can. So the absence of ammonia doesn't necessarily mean there are oceans. It could just as easily indicate a magma ocean.
To test their theory, the researchers developed a new model called the solidification shoreline. This tool connects the amount of energy a planet receives from its star with the star's effective temperature. By plotting known exoplanets against this framework, they could estimate whether a planet was likely to have maintained a magma ocean since formation.
Using the Proteus model to simulate internal heat dynamics, they found that 98% of sub-Neptune exoplanets fall above this shoreline. That means they receive enough stellar energy to keep their interiors hot and molten, rather than allowing them to cool into solid bodies.
For astrobiologists and exoplanet hunters, the implications are significant. The Hycean world hypothesis had offered an enticing vision: planets that might host life in vast subsurface oceans protected by thick atmospheres. This new research suggests that vision may have been premature.
It's important to note that this doesn't close the door on water worlds altogether. It simply urges caution against over-interpretation and reminds us that planetary evolution can take multiple paths. As Calver and his team make clear, the lack of reliable atmospheric mass data across many exoplanets limits current models.
While this conclusion might seem like a setback, it actually offers a more stable foundation for future research. It's better to have a realistic understanding of what these planets are than to chase false hopes of habitability.
Exactly. Science progresses through these kinds of corrections and refinements. We're building a more accurate picture of the cosmos, even if it means letting go of some earlier assumptions.
And Anna, for our final story today, we have something both beautiful and sobering: a glimpse into the future fate of our own sun.
The James Webb Space Telescope has captured stunning new images of the Helix Nebula, one of the closest planetary nebulae to Earth, and what it reveals is absolutely breathtaking, Avery.
Also known as the Eye of God, the Helix Nebula is located about 650 light-years away in the constellation Aquarius. It's the result of a sun-like star that exhausted its nuclear fuel and shed its outer layers into space, leaving behind a dense core called a white dwarf.
Webb's near-infrared camera captured pillars of gas that look like thousands of comets with extended tails, tracing the circumference of an expanding shell of gas. These structures form when blistering winds of hot moving gas from the dying star crash into slower moving, colder shells of dust and gas that were shed earlier in the star's life.
What makes Webb's view so special is the level of detail it reveals. The image shows the stark transition between different temperature zones: hot ionized gas near the center where the white dwarf sits, cooler molecular hydrogen farther out, and protective pockets where more complex molecules can begin to form within dust clouds.
The color in the image represents temperature and chemistry. Blue marks the hottest gas being blasted by the white dwarf's radiation. Yellow regions show gas that's cooled as it moves away from the white dwarf, and the coolest material at the edge of the nebula appears red.
This isn't just a pretty picture, it's showing us stellar recycling in action. The gas and dust being expelled don't disappear. They're incorporated into the interstellar medium, enriching clouds with heavy elements forged in the stellar interior. This is the raw material from which new stars and planets will eventually form.
According to NASA, this image is essentially a window into our own future. In about 5 billion years, our sun will enter this same phase, creating a similar nebula as it fades into a white dwarf.
The Helix Nebula has been imaged many times over the nearly 2 centuries since it was discovered by both ground-based and space-based observatories. But Webb's near-infrared view brings unprecedented detail, revealing structures that were invisible to previous telescopes.
Scientists can use these detailed observations to refine their understanding of stellar evolution, how stars end their lives, and how they distribute the elements they've created back into the galaxy. Every shell of gas represents a different episode of mass loss, creating a timeline of the star's final stages.
It's a powerful reminder that even in death, stars continue to shape the universe. The atoms that will one day form new worlds, perhaps even new life, are being forged and distributed in nebulae like this right now.
It's both humbling and inspiring to see our cosmic future laid out so clearly. The Helix Nebula shows us that endings in space can be as magnificent as beginnings.
And that wraps up today's journey through the cosmos. From terraforming dreams to atmospheric water harvesting on Mars, from X-ray catalogs mapping millions of cosmic sources to earthquake sensors tracking falling satellites, we've covered incredible ground today.
We've also learned to be more cautious about those exciting water world discoveries and witnessed the beautiful death of a sun-like star through Webb's remarkable eyes. It's been quite a day in space and astronomy news.
Thanks for joining us on Astronomy Daily. Remember, you can find us at astronomydaily.io for all our episodes, show notes, and more space news.
And don't forget to follow us on social media at Astro Daily Pod. We love hearing from our listeners about what stories excite you most.
Until next time, keep looking up.
Clear skies, everyone.